Hello, everybody. Welcome back. So, continuing from the session that we had earlier. So last session we did talk about the basics of R. Essentially, talked about how to set up the environment. Looked at some of the basics of vectors. Some of the core concepts of R, which makes R extremely powerful, namely the sequences, repetitions, right, the vectors, right. And we also looked at how to read files, consume the files into a so-called spreadsheet-like structure called as data frame, reviewing as to what the data frame has to offer, what are the types of the variables within the data frame, looking at so-called the factor variables, and understanding the structure of the data frames. We rounded off the session by doing some exploratory analysis and some munging of the data, namely adding some columns, and basically doing some distributions of the data, binning the data, assigning new variables, as I mentioned. And we also studied a little bit about the deficiencies in the data when the data contains nulls. As to how to go about reviewing those cases, and we finally looked at some matrix related multiplication and some basic in portfolio math example. This session I'm going to talk about take a real life data example and go through the process of data analysis in greater detail. Right from evaluating the structure to loading the files, you looking at the visuals of the data, how they're distributed, and also exploring some of the basic visuals that are out there, and then eventually just inferring something useful from the data. So the data that I've selected, there's a popular website called as this UCI machine learning repository. If you Google it, you'll find it. There's numerous data sets that are available. I was able to pick one of them, and the bank marketing data is the one that I've chosen for this particular session. The organization of the data is summarized in this text file by the people who made this data available. So essentially, this is a data related to how basically some of the economic factors that affect everybody influences as to whether the client is eventually going to buy term deposits or not. So as you can see, the number of variables are listed here. There are a lot of variables, namely age, marital status, education, housing, loan, all that kind of good stuff. And then finally you have an output variable which indicates as to whether the client eventually selected to go with the term deposit offered by the bank or not. And they're given some detailed information about the data set. One can take a look at it and really take deeper into that. So as you can imagine, prima facie, mainly most of the variables are categorical in nature. There are not too many number kind of variables. The idea is to maybe draw some distributions based on the intersections of some of these variables and see if we are able to generate some meaningful patterns, or at least help you look at this data set and help you visualize this data set, and potentially this can be taken to any level of complexity. So this is a brief introduction about the data. Going back to our studio, I have listed all these R files will be shared with you folks so that you can take a look at it, execute the commands independently, and really learn from learn as a follow from the session. So hopefully you will find this useful. So first is so obviously there is a CSV file, and I've downloaded the CSV file. In this case, it so happens that the CSV file has a separator of semicolon. So that's what I'm going to use. I'm going to run this. I was able to load the. I'm creating a data frame called as bank marketing. So let's quickly evaluate like the structure from the session last week. Last time, I'm sorry, I was telling you that the structure variable, the structure command is very useful. It kind of almost gives you that high level view into what is the overall structure of like basically a given variable. As I said earlier, this is a data frame carrying 41,000 odd observations. There are 21 odd variables, and as you see, it has correctly coded most of the variables appropriately. For example, factor variables. These are all the factor variables. And it is kind of giving you the levels as well, right? For example, there are 12 distinct values of jobs, 4 distinct values of marital status, 8 distinct values of education, and so on and so forth. Some of the key important variables of interest are this y, which has a binary flag, yes or no, which kind of details as to whether the client actually selected the term deposit or not. So going by looking at the summary as I said gives a detailed information about all the variables that are there in the data frame. So here it is, in the case of factor variables, it actually lists down the frequency. In the case of continuous variables or numerical variables, it actually lists the percentiles, the quartiles, just to give you a idea of the distribution. So you're just getting a view into what these variables are. The dataset also talks about some unknown values. For example, unknown marital status of unknown is coded as unknown. So default status, whether like the person had defaulted in the past, is kind of unknown for like a large portion. It's a very small portion of yes, which is good, but like which is kind of surprising as well that it is that low. So you can draw some quick inferences from this summary. If you want to clearly investigate as to what's happening with the data set, you can just do a head to understand what kind of like data set, what values are there, just to give you a quick feel for the data. But sometimes typically what we tend to do is the first 5 to 6 rows, like, and they typically tend to have a pattern. You'd really want to have like some kind of like some kind of a random selection of records, so that you're able to get a good feel for the data broadly. So there is this command called a sample command. We'll try and execute this in stages. So as you can imagine, 1 to a number of rows of bank marketing is like, basically it will generate a series of 1 to 42,000. And I'm asking the sample command to basically kind of pick like 20 from that vector, 20 let's say elements from that vector, and the aspect of replace equals false is you don't want basically any repetitions in the sampling, right? So you want like all those elements to be unique. So essentially I'm going to run this and I'm going to just like select some sample indices, right? And in this case it has chosen like some of these random ones as the indices. So all I'm going to say is I'm going to ask R to basically bring all the records that are corresponding to those indices. So if you see, this is kind of like almost like a random view of like the data, which is giving you some sense of what the distribution is. You're not really biased by actually looking at like the first 10 records of the data set. Just an innovative way of like looking at the data. So you are like running the sample command, identifying the indices. This could have easily been 200 as opposed to like 20. So and it makes it like interesting for one to kind of like look at the distribution of the data set. So sometimes like you would be curious to know what is this like factor variable, what are these so-called categorical variables, right? So let us kind of dig deeper into that category. Let me start over. Okay, So we saw this job variable has 12 levels with like admin, blue collar, and like the other 12 that make up like basically the different job levels, job types, right? So if you want to understand for a factor, for a variable that is coded as factor, if you want to pull out like let's say the distinct values of that variable, you just issue a command called as levels. Levels will give you all the 12 possibilities for that particular categorical variable, that factor variable, and those are the 12 that have been listed here. So typically what you want to do, what you would like to do is almost understand the frequency distribution of these variables, right? So here you see I just ran a table command for that job variable, and the table command gave me the numbers against each one of those job categories, right? Sometimes you would want to kind of plot this and see how the visual looks like, just to kind of get a feel for that. So again, so this is just a distribution of this as to how many people are there in each category. So you can see admin by far kind of like has the highest number in terms of the job description. So now I would like to kind of create like a factor variable and append it to the data frame, right? So this is typically what you'd like to do, right? Like once you get the data set, you would want to add your own columns. You want to like introduce your own, let's say, analysis and stuff. This is in the same lines. Here I'm trying to introduce like a variable which carries 5 categories. I'm just making this up. So it says cat 5 times and sequence 5 times, and if you remember from the previous session, paste is almost analogous to concatenation of the data set, and pasting basically kind of concatenated that, and these are the categories that are out there. Now I need to generate I need to basically distribute the data set with these 5 categories. I again call upon the sample command. Sample command will look at these 5 categories, and it'll generate so many samples, which is equal to the number of rows in the data set itself. And here if you notice, I'm making replace equals true. So obviously there are 5 possible values that need to be distributed across 41,000 odd rows. So obviously you're going to basically distribute that whole thing. So let's kind of go ahead and do that. It actually kind of generates a random combination of so we can go ahead and take a look at it as to what it actually generates. So if you want to really look at how many rows it has generated, just run the command. So I need to first create this variable and then rerun the command. So if you see this, it has created those 41,000 odd rows. So I'm just going to assign this to a new variable called as a new variable. I'm calling that as new variable. So let us evaluate the structure of that new variable. I'm just going to. So as you see, it is actually a character array, and it is saying it's a character array of 41,088 odd rows. So obviously I want to convert this from a character to a factor variable. So we just use some of the conversion functions. As dot factor new variable basically converts that into a new variable. So now if we just rerun the same command, so it basically says there are 5 levels. It automatically identifies the distinct values and basically identifies that. And another alternate way of doing this is, so new variable, so it levels new variable will also kind of bring that up. So that's the levels. So let me append this to the data frame itself. look at the command bank marketing dollar new variable equals new variable. New variable happens to be the variable that I just created. I'm calling the column as new variable itself. I'm assigning the new variable and just checking whether that variable is indeed part of the data set or not. As you see, this a new variable is definitely part of the data set. Next, let us look at some continuous variables, and age I think is one of the continuous variables that you can actually look at. So let's kind of like quickly understand. Okay, so that is rightly kind of defined as a character, an integer array, and it has like basically integer values. So typically when you have like continuous variables, you would like to first understand like as to what kind of distribution it has. And you would typically like run a histogram, right? Or you would like basically slice up that particular column into buckets and try to evaluate like basically the distribution of that. So let's run the histogram on the age column just to see what kind of a distribution we have. Okay, so as you see, so it's a pretty skewed distribution. So in this case, if you want to be specific, it's almost like a right skewed distribution, if you will. And if you have to infer, I think like basically the median is somewhere in the 35 to 40 range, and so on and so forth, right? You can like make some inferences based on that just to understand. So if you want to kind of get like some frequencies, right? Like not the frequencies, like here you have the numbers, like if you want to get the percentage of population, you can do that as well. So as you see, it's like basically kind of like it will give you the percentage population here in the density. You can use that just to kind of get a feel for like what is the percentage of the overall population that actually is represented by a given tower or a given slice of the data. So typically that's how you would evaluate the continuous variable, just to understand what's happening there. So just for fun, I'm going to introduce another variable called a salary. In this case, I'm introducing some new concepts here where I'm just saying generate basically like normal random variables, right? And I'm just going to spend like a half a minute or a minute on this, right? On as to what this R norm is all about. So these are all basically norm stands for normal distribution, right? Normal distribution is one of the famous continuous distributions that is out there, and basically a similar kind of a structure exists for the other probability distributions as well, right? I'm pretty sure you are aware of binomial distribution, you are aware of Poisson distribution, you are aware of the famous student T distribution, which is used in statistics, the so-called sampling distributions like chi-square, T distribution, right? So these are like the distributions, and every distribution has like a similar structure, right? If you see the usage, right? So for specifically for normal distribution comes with like basically two parameters, right? One is basically the mean and the other is the standard deviation, and those are used to almost like generate like the distribution itself, right? So that is extremely useful. And R comes with these four functions, right? D distribution. D stands for density, right? Like which is a probability density. And as you know, the area under like any curve, area under a normal distribution should add up to 1, right? So this generates the density of a based on a given distribution type, right? P norm will kind of like answer the question saying, hey, if you have like a value, right, now what percentage of the population actually lies below that, right? So P norm is also, you can think of that as so-called cumulative probability distribution. If the total area under a distribution is like 1, so what is the area that is covered by a given value, right? For example, let us take an arbitrary value, like this is a normal distribution with mean 0 and standard deviation 1, right? So what is the area covered covered by the value which is like represented by 0.5. Like let's say anything under the normal curve, which is like basically like which is below the 0.5 area, which has kind of swept that under that normal curve, is basically the total area that is covered so far, right? It could be 70% of the overall thing, so it would give you that that figure. Q norm nothing but like gives you the quantile, right? Quantile values. If you specify basically the probability, it will give you the quantile, and then R norm will actually kind of generate like random variables which are distributed normally, right? So I'm just like using the R norm variable. I think we'll cover this one in some detail in the future sessions, but I just want to kind of briefly introduce you to this, because this is another powerful aspect of R that one tends to use. So I'm generating here basically 41,000 odd normal random variables with a mean of 25,000 and a standard deviation of 10,000. Right, so that's the random name variable it's going to generate, and I'm going to assign that to the variable called as salary. Let's do that. So now, so let us quickly understand the distribution of this. Obviously, like we just pulled it up from a normal distribution. Essentially, I would expect that to be a normally distributed variable as well. So, and yes, indeed, it is actually pretty normal, and you can almost play around with like basically you can play around with the bin size and make it like really small, so that you actually get a smooth curve. And there are functions in R that I would like you to explore, which will help you kind of draw density, right? Which is density is just like basically a curve, right? And if you ever were to integrate basically that data, that entire area under the curve, that would actually add up to 1. Right? That's why it's called as a probability distribution, because the entire set of probabilities need to add up to 1. Just few basics of the probability. So I just added that particular variable. Now I just want to create an additional column. So here this is a contrived example, or like a variable I would say, where I'm just saying so this month actually specify the month in which the customer was contacted by the bank. I'm just dividing that into two halves, two yearly halves, right? Half yearly buckets, right? I'm just saying first half and second half. It's a simple if-else statement. It is saying if the bank month is in any of these values in the vector that is mentioned here, then obviously that becomes true. Then basically kind of call that as first half. Otherwise, basically default that to a second half. That's what it says. Let's go ahead and run this, and let us create an additional column called as year bucket. So that's kind of it. This is what you typically tend to do. You get a data set, you analyze it, you create more columns, you add more columns to it. Like some columns you actually introduce like continuous variables. Some columns you tend to almost like create categories, right? Based on existing columns, based on some existing rules, right? You might want to create like additional columns, so that it will help you do further analysis on. So now let us look at some proportions. So let me run the table command to understand the intersection between education and the marital status. Let us look at as to how this is actually looking. So these are all the different levels of education, and these are all the different marital statuses. And these are all the different numbers for this, right? And this by itself sometimes is not really useful. You would want to kind of get the marginals, as well as want to kind of get like a percentage of the total population, or the percentage of the row, or the percentage of the column, any one of those things. So typically you would want to so there's a command called as prop table, which is nothing, which stands for proportion of the table, and we will just execute that. So if you see this is actually, I multiplied that by 100 to kind of give us percentage numbers. To see this, it will give you the total percentage will add up to 100. Like the total of all these numbers will add up to 100. That's a useful thing to know. But I would like to kind of know. I would like to know based on a given row. Right? If you see this, this is actually adding up to 100%. Right? Now this entire row is adding up to 100%. So that's the row percentage. If you want to do this by column, you can do that by column as well. So in this case, that the divorced, it's kind of like adding up to 100%. There's something called a mosaic plot. I'm not really a big fan of this, but like I tend to use this once in a while. It's kind of gives you a good feel for. It's almost like a percentage, like stacked bar chart. But it'll kind of give you a two-dimensional view by virtue of the size of the bars and their lengths, right? As to how they're distributed. So kind of useful sometimes to look at like some of these charts. So now this is a this will let us now do something interesting. As I said, let us introduce some cuts, right? And let us do something slightly more complicated. I want to generate like a sequence from -2 to +2 with increments of 0.5. Let us kind of go ahead and run that. Let me clear the Control L, will clear the console. Sequence, I'll generate the sequence -2 to +2. I'll call that as the standard deviation cuts, right? The idea for me is look at the salary variable and just generate basically cuts that are basically 1 standard deviation away from the mean, 2 standard deviations away from the mean, -2 standard deviations away from the mean, and what have you. That's the idea. So if you see this, so if you understand the mean of the salary, so this is actually, I'm just going to execute that. Mean of the salary is 25,041, and then SD cuts is actually a vector which is carrying approximately 10 elements, I guess, right? The idea is, so if you see this, mean is just a single number, SD cuts is a vector, and then SD of this FD of the salary is also a single number or a scalar. So when you actually run this command, since this SD cuts is a vector, it actually generates basically this, and it creates like so many different numbers, right? So it generates numbers. It will add this scalar into this vector, and vector multiplied by this, and it creates this so-called vector, which basically covers what is the deviation that is defined by the SD cuts, in the cuts from the mean itself, right? And we almost defined a cut array, almost as to how we want the bins to be formed, and these are some of the breakpoints of those bins, right, if you will. Just to make this complete, you would have to introduce the minimum and the maximum, so that the bins are complete. So now that you have the cut points, the next command is you would want to kind of break the salary variable into those buckets, right, that are defined by the cut array. And then you are saying labels as false. Labels as false will just kind of almost enumerate. Enumerate is the wrong term. Basically, it will almost generate a sequence numbers for each one of the buckets that are out there. Let's go ahead and run that. So I never ran that. So I ran the cut arrays. I'm adding the minimum and the maximum here, and then I am basically creating the salary cut. So I just want to quickly visualize as to what that salary cut has to offer. And if you see, as I said, it actually created 10 buckets, and it just named them 1 to 10 without giving any meaningful kind of names to that. You can specify the names. You can basically identify an array and give a name to it, so that you are able to use it. In this case, I'm not going to use it, but you can use the labels function to kind of specify the labels that you want like those bins to have. So I plotted that. So here it's a different flavor of the same command, but I am like using the label. I'm dropping the labels thing there, and if I run the salary, if I run the plot command again, it generates like basically all these ranges which are hard to read sometimes and stuff, right? So that's the challenge. You can always kind of like rename it later. So I really at this point in time don't want to create anything manually, so I'm just going to identify. I'm going to create like this, break the population into 10 percentile buckets, right? And then like let us see what it actually generates. So as you see, the percentile buckets, like it almost slices the population equally, right, into 10 buckets, and it'll give you the ranges and stuff. And this is kind of sometimes useful to know how it is. The rationale behind showing all this stuff is there are multiple ways of slicing, right? You can almost take a view that, hey, I want to identify outliers as one bucket. Outliers both basically on the positive side as well as the negative side on one bucket, and you want rest of the stuff which is so-called you define as normal set of values as another bucket. You could have it as 3 buckets, and then you could understand how those 3 buckets are basically playing with other variables, if you will, right? So those are the things that you typically tend to do with the cut command and creating the bins and the intervals, just so that you are able to do a deeper analysis on that. Okay, so now just wanted to introduce you to some of the looping routines that are there in R. So here what I want to do is I want to generate for any numeric variable that exists, right? I want to generate like a percentile distribution, right? And the percentile distribution is do a distribution from all the way from 5 to 95%, right? At the step of like 5% each, right? That's the percentile bucket that I'm talking about. So the idea behind this is basically let's kind of step through this statement itself, right? So I create a data frame and I call it quantiles and like basically the percentile buckets, right? Here just need to run that. So if you see this, this is I created a data frame with one column and I call that as bank marketing distribution. I'm just gonna assign that. I'm gonna run this. So this is almost like some empty set of variables that I have generated so that we are able to add those corresponding columns. So the next is I want to loop through all the columns. That is the function that is the loop that I'm trying to write here. So for all the columns that are there in the data frame, so for example, call names bank marketing 1 to whatever length, right? Length of call names bank marketing, column names of bank marketing will give you whatever is the column names, which is 21, right? So it will loop from 1 to 21, right? And 1, 2, 3, 4, 5, 6, so on and so forth. And then it will identify as to whether a given field is numeric or not, right? It is basically checking as to whether a given field is numeric or not. If the given field is numeric, then it actually generates the quantile function, right? And you guys saw the quantile function in the last class. The quantile function will basically generate numbers for that column, right? From 5% all the way to 95% as to what is the value. The idea is it will actually append that to the banking marketing distribution, and the banking marketing distribution had values like this, quantiles, right? So let's go ahead and run this for loop. So I hope this is clear. Essentially, this for loop is looking at, like, it is iterating through all the column names of the data frame, and it is picking out like those columns that are numeric in nature, and for the numeric columns it is actually generating the percentile distribution, right? Like, basically, hey, what is the value corresponding to 5% of a given variable, right? 5%, which corresponds to 5% of the population of a given variable, if you will, right? What is the value associated with that, or 50% or 75%? So that's what it is actually giving you. So it actually does that. Let's go ahead and run the for loop. So it ran in no time. This is one of the advantages of R, that, like, typically writing a macro and other things in Excel sometimes is kind of like tedious, and you have to really struggle with it sometimes. So this is much simpler, and it is much faster as well once you kind of get used to it. So now if I see this banking distribution, if I were to just so if you see, it has given like some weird names and stuff. So I wanted to kind of get rid of that weird names. So let us go ahead and do that. And this column array, I have been collecting the names of the columns which are numerical in nature into this particular array. So let's quickly investigate that array, and those are the fields that are actually part of the array. So I'm going to reassign basically the column names. So this is how easy it is. And then if you were to just like look at those columns, so again, column numeric is like, and basically it gives you the column IDs of those numeric fields. So here here is a case where I just said, hey, like, just give me some sample values there. And then banking market distribution carries all those different fields. So from 5% to 95%, it has generated the values for all the fields, right? So the other command that I wanted to quickly show it to you guys, which is very useful, one was of course the quantile command, right? And you guys have seen this in the last session. This is called the column bind function. Column bind is nothing but, like, if you imagine a data frame which is equivalent to an Excel, you're just almost appending a column to that, right? So that is column bind. And a similar concept on the row side, you could call that as row bind, R bind, right? R bind and column bind. These are extremely useful for you to keep on appending to a data frame. We've already seen one way of appending to a data frame, right? So this is another way of appending to a data frame. You're kind of like binding an additional column, right, onto an existing data frame. So next, so typically what you tend to do, right, once you're done with analysis, you want to write that to an CSV file, and the command for that is fairly straightforward. There are other formats that you would want to write, but I'll leave that out for now. But typically you would want to write, like, almost your matrices into a CSV file. So I'm just going to go ahead and do that. So you write.csv to a file. As I had explained in the earlier session, I typically tend to create like folders so that we are able to organize this. I encourage you to create folders, otherwise it can get really messy, and you'll not be able to differentiate things. At a very high level, you can think of a structure which would have input files, which would have your R source files, which would have output files, right, which would have images, right, which would have something of that nature, right, now, which would have presentations, which would have some R markdown files, which are where you can actually specify, you can type into it and stuff like that. So typically these are the things that you can tend to do, and so far we have introduced some columns. We have created some buckets for a column that we had already introduced. So now let us look at some plotting techniques. So I'll just take a minute in terms of organizing your thoughts around what this ggplot is all about, right? And some of you might be familiar with like Tableau and ClickView and all this visualization software. If you look at this like software, like when they are like oriented based on the so-called layers, right? And the layers, right? You could have like, I mean, if you generate a scatter plot, you can vary the size of like basically the point based on some third variable, right? Or you could color that like basically this one based on the third variable, or you can change the shape based on some fourth variable, right? Those are all layers that you are kind of tacking on to the same chart, and similar kind of concepts are available in R as well, in this package called as ggplot. Ggplot is, I think, an extremely powerful package. I think I would argue that like basically for doing some commodity kind of like, let's say, visualizations which are like useful for your like analysis, right? Where you want to generate like tons and tons of like graphs and stuff. This might be actually more productive way of like doing this, as opposed to like dumping this into a Tableau and like, I mean, bringing the data back and forth and so on and so forth, right? So yes, Tableau and ClickView are great eventually for you to present as to what is the distilled version of like the so-called analysis that you do in crisper, like, I mean, very sharp like visuals. But in order for you to do those tons and tons of like visualizations, for you to like really understand this, so ggplot is maybe a recommended way, right? I tend to use that a lot, and I have a bias towards it. There are other packages in R which give you similar kind of flexibility, but I think ggplot is by far like, I mean, the most advanced, which can give you that flavor of adding on layers, having the flexibility in designing your like, I mean, visuals and stuff. And I would strongly urge you to spend some time in playing around with the visuals, playing around with the examples, and potentially extending your knowledge in of using basically ggplot. And it gives you extreme flexibility. And the other I basically want to highlight is like, I mean, obviously Tableau comes at a cost, and this is free of cost, and like, I mean, you would want to really make use of this opportunity to like really move your projects forward, right? Sometimes these produce actually kind of publication quality, like, I mean, graphics and stuff, so which is useful. So let us draw some plots. So let us quickly understand the structure of like, I mean, ggplot, and they have something called as aesthetics. Like, I mean, aesthetics, you can think of aesthetics of a graph as, hey, you have a x, you have like an x-axis, you have a y-axis, right? You'll have to define that, right? So you have a color aesthetic, you have a shape aesthetic, you have like a basically if you have like multiple, like, let's say, colors being represented, you have like basically you could have shapes, you could have colors, as I said, you could have size, right? So those are all the different aesthetics. You have like colors that you fill into certain shapes, right? So those are all the different aesthetics, and you have the ability to mention different variables to kind of cover all those different things, and I'll show those different flavors to you in these plots. So the syntax is fairly straightforward, nothing to be worried about. So let's kind of like follow through this, right? So, and the great thing about this is you can add more layers as you kind of like, you can piece together like basically the graph incrementally, right? You don't really have to kind of get everything in one shot, right? So the syntax for that is it actually accepts a data frame, or a vector, or anything that works, and in the aesthetics list, right, it almost like you have to specify what aesthetic you want to kind of specify. Here I'm saying, hey, on the x-axis basically mention education, and on the y-axis let's look at the continuous variable which we just added as a salary, right? And I'm just saying, hey, that is like the base information. I'm also saying, hey, why don't you generate like a box plot of this, right? And because continuous variables, I would like to understand the distribution by education of the salary, right? So let me go ahead and just run this portion of like the command. And if you see this, this is like this is a box plot. So I know this is like a contrived example with and the ranges of salary and stuff. There are like really some huge outliers, right? But like largely, basically, this is a pretty tight distribution with the center line giving you the median, right? And the median is the center line, and this box is kind of almost giving you the 25th and the 75th percentile, right? For each one of those, right? And it's almost like, I mean, the range is pretty much like, I mean, the same, right? So you tend to use this plot to almost kind of get a quick view into how the variables are distributed based on different like slices that you would want to look at, right? Here in this case, I've decided to look at it from an education standpoint, and I see that like, hey, okay, so this makes sense, and there seems to be the illiterate buckets who seem to be kind of carrying higher salaries, which is kind of counterintuitive because this is all kind of made up data, right? Again, so those are the things that you typically tend to see in this setup. So now, while I have seen this, I would like to kind of almost like say, hey, like let me see this like based on the marital status of the customers that I'm dealing with. And scales free equals y is basically, it's almost like I'll show you what I mean by that. So now, so there are 4 marital types, as you might recall, and this is almost like created those 4 panels to show how the data is distributed, almost like box plots for that. So if you see, like, I mean, this whole unknown bucket, like, I mean, is carrying is like really kind of off in terms of distribution, while rest of the stuff is all pretty neat and tidy, right? With this divorced category kind of having higher like levels, if you will. So those are some of the broad inferences that you can make, right? And just to pretty up the chart, you can provide like, I mean, label for the x-axis, y-axis, title and stuff. And when I say scales equals free equals y, right? If you see, you want to have basically the flexibility of, one is you can fix the scale so that you can get like, I mean, you can get the same y-axis for all the 4 quadrants, if you will, right? And then you will be able to kind of compare it. Sometimes those charts, like, I mean, tend to be inflexible or difficult to read. Sometimes it's difficult to sometimes it's easy to let this the axis scales kind of float, so that you are able to kind of have meaningful charts kind of displayed, right? So you should like, definitely I encourage you to play around with that, remove it, or like, I mean, make it scales. You can alter the x-axis as well. In this case, it doesn't make sense for us to alter the x-axis because it's a categorical variable. So you can play around with that, and there are some cool things about like the graph that you want to alter. You want to assign the labels, the title, and you want to almost see this at the bottom. This is all overlapping, so you would want to fix that by rotating the axis ticks and the labels. So, and now the chart looks like, I mean, that much more tidier, and this is like a chart that you can pretty much paste into your presentation if you want. Now let us like, I mean, look at a slightly more interesting graph. So I want to look at like a scatter plot. So scatter plot, I'm going to use basically a type of chart called as like a point chart, like in ggplot calls it a point chart. So there are 2 continuous variables, age and salary, and then I'm saying the points you basically color by the variable y. If you recall, the variable y has 2 flavors, yes or no, right? Which is whether the client accepted the term deposit offer, or like they declined it, right? So I would like to kind of like know the distribution of that. I'll run this command, a similar kind of command as to the last one. Again, I'm just wrapping the chart by job. Okay, so let's run this like phases by phases. So this is the overall distribution, and if you see the red one stands for no, and the blue one stands for yes, right? And I can see the how it is distributed. So now if I want to kind of if I want to know how this is distributed for every job type that is out there, I could do this. And it actually kind of shows you the distribution. And if you see this chart, this is kind of almost hey, this age is on the higher side, and those are all retired people, right? Age is on the higher side, and they seem to be kind of they seem to be having a higher proportions of yes, I guess, right, compared to some of the other areas, if you will. This and this seem to be having a higher proportion of yeses compared to others, and this I think definitely has a higher proportion. So I'm just going to complete the graph and have some headers to it and stuff, and this makes it interesting. So next is okay, so I have this okay, so let me understand if there is any linear relationship at all. Looks like there isn't. It is all over the shop, but I'll go ahead and add a linear relationship nonetheless, right? And then I want to add three types of let's say linear regression lines. One is I want to consider the overall population, right? And the other is I want to consider the grouping. I want to consider a regression line for each one of the levels of y, that is yes or no, right? For example, each color I want to kind of run an independent regression line for each one of those colors, as well as have an overall let's say regression regression line for the entire population, if you will. So I'm going to do that. So the way for you to do it is not only that, here if you see I've added basically geom smooth method is equal to lm stands for linear regression, linear model. So method is equal to lm stands for, essentially what it does is it actually kind of takes it's already segmented by y. It actually creates a line. It creates a line for each one of those y's. So let us kind of run only that just to see what it actually churns out. So if you see, so we have not segmented by anything, so it has actually generated there are three, actually two lines there, one for the yes and one for the no's, right? Unfortunately they are indistinguishable because they are so close to each other. And then let's say if I add this additional thing on top of that, so I have another line that actually kind of came in, but this will be more powerful in in other scenarios, I would imagine, which will help you kind of almost show how the data is behaving, right? Is there any linear relationship at all, right, to this whole to these set of variables that we have chosen. So now I want to kind of take it in the full distance, look at the same thing based on three separate things. And as you can see here, the three colors become evident, right? At least if I look at this, there is a downward trend here, there is an upward trend there, right? And the overall population of that, right, the housemaid population is kind of almost flat, which is determined by the blue line, right? So you can see that hey, you can generate really complicated graphs using this, and draw some inferences, right? You can write you can start writing statements, you can draw some things, right? You can look at tests of significance. Hey, okay, so this seems to be an area that I want to focus on, this seems to be a retired area that I want to focus on. You could dive deeper into that and investigate a little bit more. And lastly, just to change the flavor of the graphs, we have been looking at scatter plots, we have been looking at box plots, we looked at histograms. I want to change this up and show you basically a 100% bar stacked bar chart. So there, if you see, the aesthetic that I'm trying to fill is the marital status. I want to say, hey, give me the overall numbers for for every job type, but within each of those actually fill it up by the number of people with different marital statuses, right? So, and I'm just going to basically say position equals fill. That will actually kind of help me generate a 100% stack bar chart. Let me kind of go ahead and run that. Let me only run the initial piece. If you see here, so it's fairly straightforward for us to understand. So admin, this is how the distribution is, right? Now position equals fill. It generated in the 0 to 100%, right? Now 0 to 1 in this case. And you can actually specify a different color palette if you don't really like it. So there are all this kind of there are all these flavors in which you can specify what colors you can play with, right? And stuff like that. For example, in this case, the fill colors is what we want to wear, what we want to change. I want to move that to a different palette altogether. I can do that, right? I can change the palette, if you will, and we can play with this all day long, right? If you want. The idea is, okay, so if you want to really split this into multiple panel plots, you can actually do that and draw some interesting inferences from this. So okay, I'll just end here. So this is what we learned in this session. So we took a real life data example. This was a data that was available freely on the web from bank marketing. We loaded the data, we investigated the structure of the data, we understood the difference, right, between continuous and the factor variables. What are the different columns? We added more columns to it. We added a continuous variable called a salary. We added we added a column which communicated yes or no, right, based on other columns. We actually split we created a category based on some other column, right, and we did a whole bunch of visuals to understand the interplay of different variables, right, and then eventually we actually wrote the output from some of the distributions that we generated into a CSV file. So you got an introduction to a bunch of things that you could do, and typically this is what you end up doing, right? You load up data, you analyze the data, then you find something interesting, you save all these different plots, right? For example, in this case, you could export the plot and save that as PDF, right? And there are commands where you can actually specify a bunch of graphs and then save a bunch of graphs into a PDF, right? You can export this as an image or this, and you can embed that into copy that into a clipboard, paste that into a PPT. You can do whatever you want, right? You can do all that stuff. You can flip through all the images that you have generated during the course of the session. I'm just doing that right now. You can generate all this, you can save all this stuff if you want, and use that for further analysis. So typically these are the things that you tend to do: draw distributions, draw graphs, draw copious graphs, so that it will help you understand the distributions and help you almost develop develop how the data is organized, so that you can structure your further analysis based on that. So I hope you found this to be useful, and I look forward to doing another session which would take a look at the stock prices and do a similar kind of analysis using the stock prices. Thank you so much.